So our parameterization of surfaces with two variables gives rise to a new way to think about surface area. So let's say there's this surface that lives in three-dimensional ambient space. It's a two-dimensional surface. And we have a point on there. And remember, we're thinking like in the previous video about UV space. And maybe I should have drawn this picture in the previous video. But we have a tangent vector in the u direction and a tangent vector in the v direction. And if we go small enough, then we can think of our surface as being patched up by tiny parallelograms. And really it's, we go just du in the u direction and dv in the v direction. That's just really small amounts in both directions. But we go along these vectors because close to this point, our surface is approximated by the tangent plane. Okay, and then in Math 126, we learned that the cross product of two vectors, if we take the absolute value of the cross product, or magnitude of the cross product, then that's the area of the parallelogram. So that's how we can approximate dA. And then du and dv we can just think of as scalars. So we have this formula. dA equals magnitude of Ru cross Rv du dv. Okay, so for example, let's say we want to find, let's do one that we know so we can compare to what we had before. So find the surface area of the paraboloid z equals x squared plus y squared, such that x squared plus y squared less than or equal to 1. So what's happening there? We have this paraboloid, z equals x squared plus y squared, and then we're confined in this region. So that's a circle of radius 1. We're confined within that region. And we want to find the surface area of basically that bowl. Okay, so how do we do this? First, we need it in an R format. Here it's pretty easy. If we already have z in terms of x squared plus y squared, or in terms of x and y, then we can just parameterize it with x and y. We can use any variables we want, so as long as there's two of them. So there's our R function, and now we can actually do R sub x and R sub y. So let's do that. 1, 0, 2x, and then R sub y, taking the partial with respect to y, is 0, 1, 2y. And now we need to find the magnitude of the cross product. So let's write that down. Here's the cross product. 1, 0, 2x, 0, 1, 2y. And because that x and y are there, this 1, 0, and 0, 1 will always be here. Remember that. We'll come back to that. Let's quickly calculate that. That's 2x, comma, negative 2y, comma, 1. Okay, so if we want the magnitude of that, that's going to be the root of 4x squared plus 4y squared plus 1. So what we're looking for is the area of 4x squared, or the integral, 4x squared plus 4y squared plus 1 dx dy, and then we need bounds for that, which is kind of ugly. That's in that circle. So like if we really wanted to, y goes from negative 1 to 1, x goes from negative 1 minus, or the root of 1 minus y squared to positive the root of 1 minus y squared. That's not great. Also, this is really hard to integrate. I don't know how to integrate that with respect to x. So we would have to convert to polar anyways. Or we can just start with polar to begin with and just parameterize it differently. So what happens if we parameterize differently? This isn't the only way to parameterize this curve. What if we just parameterize it in terms of r and theta? And maybe, okay, yeah, it's fine. Maybe we'll call it, no, I'll keep it at r and theta. Maybe I'll call this curve big R. Okay. Then I could do r cosine theta, comma r sine theta. That way x and y are within a circle. And then z is actually going to be r squared. Why? Because z equals x squared plus y squared. That's another parameterization of this parabola. So just same as a plane can be parameterized infinitely many ways, except worse. A surface can be parameterized still infinitely many, but it feels like a lot more ways. Okay, so let's see what happens here. We have partial derivative with respect to r is cosine theta, comma sine theta, comma 2r. Partial derivative with respect to theta is negative r sine theta, comma r cosine theta, comma 0. And then we want to find the magnitude of the cross product. Cosine theta, sine theta, 2r, negative r sine theta, r cosine theta, 0. Okay, what is that? That is negative 2r squared cosine theta, comma, negative 2r squared sine theta, comma, r cosine squared theta plus r sine squared theta, so just r. Okay, and then what's the magnitude of that? r cross r theta. So we're looking for the magnitude of this vector is the root of, this is now going to be 4r to the 4th cosine squared theta plus 4r to the 4th sine squared theta. Okay, that's good, because that's just 4r to the 4th, plus r squared. So that's going to be the root of 4r to the 4th plus r squared. And if we restrict r to be greater than or equal to 0 in our parameterization, which we should, because if we don't, then we actually get double the surface, which is not what we want. Or maybe we get, yeah, we get double the surface. Not what we want. So then we actually get, we can take out an r. We get 4r squared plus 1. And now we can actually integrate this, because this is set up for a u substitution. So we have the absolute value of that, we have a dr d theta, and then r goes from, it's the unit circle, so r goes from 0 to 1, theta goes from 0 to 2 pi. Notice here we did not need an r dr d theta. If we actually had converted this to polar coordinates, this r would have been the r dr d theta. So we're not converting to polar coordinates. We're parameterizing in a polarish fashion. Here it's exactly a polar fashion, but sometimes it might be a polarish fashion. Okay, and then we can integrate this. I just want to go back to the first version for a second, because remember early on we had a formula for surface area, which was the double integral over the region of the root of 1 plus fx squared plus fy squared dA. And notice that if we have z equals f of xy, then we can always parameterize with r equals x comma y comma f. And then my rx is going to be 1, 0, fx, and ry is going to be 0, 1, fy. And so then the cross product will always have this 1, 0, 0, 1 here. 1, 0, fx, 0, 1, fy. Cross product will be the root of, or not taking magnitude yet, sorry. Let's actually calculate the cross product. That will be fx, comma, negative fy, comma 1. And so then the magnitude of the cross product, not r, fr, magnitude of the cross product will be the root of fx squared plus fy squared plus 1, which was exactly in the formula for the surface area. So that's good that this agrees with the previous thing that I told you was correct.